Well, yesterday we saw how to differentiate the basic trig functions. As far as integration goes, to start off with, we're basically just going to look at the reverse of what we saw yesterday. So logically, now you've got to be careful with your negative sign, mind you, because remember when you differentiated sine, you got cosine, and when you differentiated cosine, you got negative sine. So very easy to make a mistake and get it the wrong way around. When we integrate cosine, then we must get positive sine. Whereas when we integrate sine, we'll get negative cosine. Right? So be very, very careful with that. And then, of course, the third one is the one that produces tan. So if we have a sec squared, we'll integrate and we'll get tan. And again, you see, I've just written that up there for a linear function. And if it's a linear function, we'll end up with 1 over the coefficient of x out the front. But just like we did with exponential functions, just like we did with log functions, I think the idea is, hey, let's try and create the derivative of the angle, in this case, out the front, and then we know it goes back to just the sine or the negative cosine or the tan of the angle. So here's sine 3x. In this case, it is a linear function, so I can just go 1 over a. So it'll be minus, sine goes to negative cosine when we're integrating, minus 1/3 cos 3x plus a constant. Again, linear function. So in this case, coefficient's negative 5. Cosine goes to positive sine. So when we go 1 over the coefficient, we get negative 1/5 sine 1 minus 5x. And let's do a sec squared just to complete the set. Coefficient in this case is a half. Turn a half upside down. You get 2, and that one will go to tan. And just like when we were differentiating, the angle doesn't change. Let's do a definite one. You know, radians. Whenever we're doing calculus with trig functions, the angular measure is radians. We always use radians. So, integrate sine, we go to negative cosine. We'll have minus half in this case. Substitute in pi on 2, substitute in pi on 6. You'll see these sorts of answers coming up a lot. Pi on 3, all those exact values that we know. So in this case, pi is negative 1, and pi on 3 is a half, so minus 1 minus half, times it by minus half, 3/4 as our answer. Find the volume of the solid formed when y equals the square root of sine pi x. But fortunately, when we do volume, remember, we go pi times the integral of y squared. Oh, that'll get rid of the square root sign. How convenient. So y squared dx, because we're going around dx axis, sub it in, and we're just integrating sine of pi x. So pi times the sine of pi x. So pi, sine again goes to negative cosine, minus 1 on pi out the front. The pi's there will cancel. Cos pi minus cos 0, we end up with 2 units cubed for our volume. All right, so what if the angle is not linear? And let's face it, most things aren't linear. I mean, we see all sorts of functions. That's why I think it's good to think of the same idea, like we did for logs, like we did for exponentials. Let's try and create the derivative out the front. The derivative of x squared is 2x. So I want to turn my x into 2x, but to balance it out, there'll be a half out the front. So I now have it in the form of derivative sec squared of the function. So therefore, that must just go back to tan of the function. So tan of x squared, but a half out the front. Okay. Sine squared x. Think back to when we did trig last year and all those double angle results, and I said, you know, it's going to be really handy to remember the rearrangement of this formula for sine squared and cos squared. And I said to you, next year I'll remind you of that, and hopefully you won't have forgotten. Well, here I am reminding you of that. Hopefully you haven't forgotten. Sine squared x, if we want to change that into a double angle formula. Because remember, cos 2 theta, well, Cos squared minus sine squared was the first way we saw it, but then we could rearrange that to be 1 minus 2 sine squared if we make sine squared the subject, half of 1 minus cos 2 theta. If we make cos squared the subject, so they're very similar. All we really got to remember is that cos squared is the plus cos 2 theta, sine squared is the minus cos 2 theta. Okay. So now sine squared becomes a lot easier to integrate because I can now just change that to a half 1 minus cos 2x, and I can handle that integration quite well. So 1 goes to x minus cos, well cos goes to positive sine, so we'll have minus a half sine 2x. Whether you leave it factorised, I've expanded mine out, I suppose it doesn't really matter, x on 2. That is a very common question. Integral of sine squared, integral of cos squared, or some variation of that. Very common question in Extension 1 paper. It'll probably pop up somewhere because they like to see who remembers that little rearrangement. Ooh, tan x. We didn't have one for tan x, but if you remember back to yesterday, we did a differentiation question which gave us a clue. If we rewrite tan x as sine x on cos x, I now have the situation of derivative on function. Well, I don't have exactly the derivative on the function, but I can certainly create it. The function on the bottom is cos x. The derivative of cos x minus sine x. So I could rewrite that. I'll balance it out with minus out the front. I now have derivative on the function, and so we get minus the log of cos x, plus, of course, a constant. I personally prefer to write it as the log of sec x. And that's only because I don't like the negatives. So I can bring that negative in as a power, so it becomes cos x to the power of negative 1, and the reciprocal of cos is sec. So I think it's a little bit neater. It's well worth remembering that. In the exams, you get a standard integral sheet. Tan x is not on it. Okay? I wouldn't go through this process every single time just to get that. It's one of those ones that crops up a fair bit, and so it just saves time to remember the answer and go, okay, I know that when I integrate tan x, I get the log of sec, or minus the log of cos, whichever you prefer. Whoa, cos x times sine to the power of 7x. All right. Remember that idea of substitution, which we'll look at in more detail later, so don't panic too much. I can use that idea here. What is causing me the problem? Well, the problem is this sine to the power of 7. If that wasn't there, I'd just have cos x sine x, and I could change that to sine 2x or something like that. The power of 7 is causing me the problem. That's what I'm going to make u. So u equals sine x. If I differentiate sine, I get cosine. So now I can substitute that in. If I'm going to change my variables, however, I also have to change my limits, because those limits refer to x, not to u. But that's easy. I've got a little formula up here that lets me do that. U is the sine of x. So when x is 0, u will be the sine of 0, which is 0. When x is pi on 2, u will be the sine of pi on 2, which is 1. So let's sub in. The limits change from 0 to 1. Sine to the power of 7 becomes u to the power of 7. Cos x dx becomes du. And we now have a very simple little integral to do. Just add 1 to the power over the power. And so I get 8 u to the 8. Sub in 1, sub in 0, and we get our answer there. As I say, we will look at this idea of integration by substitution in a bit more detail later this term, early next term. Can't quite remember whereabouts we do it, but later on. Here we go. 14i and 14j.